Hello everyone. We are continuing our lecture on X-rays and we are going to cover X-ray diffraction and Compton scattering today. Okay, so let's get to it. Before understanding the diffraction in X-ray, we need to revise the concept of diffraction itself. So if you remember, in the case of diffraction of visible light, we need some grating, and that grating, the order of the grating must be very near to the wavelength of the light that we want to diffract. Here we know that the X-rays have a wavelength of 10 to the power minus 8 to 10 to the power minus 11 to 12. So that means we need a very fine grating, we need a very narrow grating which could diffract such a tiny wavelength. Now for a regular grating that is used in the for the visible light to diffract X-ray is an impossible task. Because if you remember, what is the wavelength of the visible light? It is 369 360, is it nanometer? I think nanometer to 4000 no 700 nanometer, right? If you want to, okay, nanometer means 360 into 10 to the power minus 9 meter. 1 2 is minus 7. So it has a range of 10 to the power minus 7 meter. Visible light has a wavelength of 10 to the power minus 7 meter. So it can diffract some of the rays if it is made a little bit smaller, but to diffract the X-rays of 10 to the power minus 11 meter is very hard job, actually impossible job for this kind of grating, which is made for the visible light only. That's why we need a grating. Now it turns out that we can use the crystal lattice or lattice, what is it called? Crystal lattice is a diffraction grating in the case of X-rays. You see, we know that the dimensions, we can say, yeah. So the distance between two atoms in an X-ray, in an crystal lattice is 10 to the power minus 10 meter. Okay, so which is very comparable to our X-ray range of wavelengths. So it was von Lower first who introduced this concept that we can use crystals for diffracting X-rays, and it was experimentally checked either it is correct or not, and it was found that it is correct. Okay, so we are going to see the experimental observation of von Lower, and we are going to see the theory behind it, and it covers the Bragg's law of diffraction as well. Okay, so let's get to the theory and the experimental bit. Experiment. Yes. So let's discuss about the diffraction of X-rays. This is the experimental setup. We have a Coolidge tube through which the X-rays are being produced, and these X-rays are passed through the slits until we get a monochromatic beam of X-ray. When we get monochromatic beam of X-ray, the X-rays are being incident on the crystal and here we have a ZnS crystal, zinc sulfide crystal, and after it strikes to the crystal, it is being diffracted and we get the result on the photographic plate. And it turns out if you expose the photographic plate to this experiment, to the X-rays for a sufficient amount of time, you would get something called lower spot. Now, if you want to know the reason for the production of lost spot, it is uh, quite deep physics. If you want me to say the reason, then I would say that lost spot is formed because of two phenomena. First one is due to the X-ray themselves, due to the diffraction of X-rays, as well as another mechanism also happens here, and that is from the crystal side. So you see, whenever we uh, incident some rays, some waves on X-rays, on some waves, sorry for that. So I was talking about whenever we apply any waves to a crystal, it turns out that X-ray are diffracted, and another thing also happens here, and that is due to the crystal. This crystal forms the reciprocal, something called reciprocal lattice zone. Okay, and as a result of these two, these lost spots are formed. So this is the reason behind it. If you want to know further about it, we can go and search about it. Okay, but I'm not going to towards that because it doesn't cover our syllabus. So now this is the experimental part. So what really goes on this part, or maybe just this part, is shown here. In a crystal, the atoms are arranged regularly in layers. Okay, and between these two layers, I have supposed the distance between these two interlayers in the crystal to be d. Let's suppose we have a X-ray and it strike to this atom P and diffract or reflect. Similarly, we have another X-ray which strike to the atom P and it reflects. Now we have understood from the interference phenomena that whenever we have wait a second, I should use another color. So if you remember in the interference pattern, we had one spot, one slit, actually two slits, and whenever we use a monochromatic beam of light, these would go up to a single point P, and to find out the wavelength of the wave of this beam of the light that we are using here, what is our first step? Our first step was to find out the path difference in between these two waves, right? So similarly, here we try to find out the path difference in between this X-ray and this X-ray. For that, path difference, and it turns out experimentally that path difference is equal to n lambda and we use the same formula in the interference pattern too. Okay, so path difference is equals to n lambda. Now, if you see here, and if I consider this length is equal to this length, that is, this is d, right? Now, if you see, this is a theta angle, which is called the grazing angle. Sorry, not a grazing angle, but I think it's called glancing angle. I think it's a glancing angle. Okay. So if you see this glancing angle theta, if it is great, so wait a second. I think it's a glancing angle. Let me check. Yeah, it is. So if we suppose theta to be the glancing angle, by using vertically opposite argument, we can consider this to be theta, similarly this to be theta. And if we use a simple trigonometric ratio, so trigonometric uh, identity, we would find that this path difference is given by d sine theta, and this one is also d sine theta. So the total path difference here would be 2d sine theta equals n lambda. To find out the value of lambda, let's suppose we are talking about first order reflection or first order diffraction, whatever you want to say it. For that, n becomes 1. For first order reflection, n equals 1. If that is the case, then 2d sine theta equals lambda. So we find out that this lambda of X-ray can be found by using this 2d sine theta formula. Okay, now we know the value of d from our experiments on the crystals. What is the intermolecular distance between the two layers of atoms in a crystal lattice? And similarly, we know theta because we do the experiment and we know where we are at which angle we are using the incident light. So, since all of these are just known quantities, we can find out X-ray very clearly or very easily. And it turns out that this lambda is indeed nearly from 10 to the power 8 to 10 to the power minus 11 meter wavelength range. Okay, so this verifies our experiment and as well as theory. So the instrument which is used in this kind of uh, calculation is called Bragg's spectrometer. Okay, and actually this calculation was first done by Bragg. Okay, so it is also called the Bragg's law. This formula is also called the Bragg's law. About so more about it, I don't think I should talk. Okay, yeah, this is it. There are some things about the spectrometer and it's easy for you to understand, so I'm going to leave it to you. Now we are going to cover Compton's scattering. Okay, Compton's scattering is very important because not only because of it is because of its importance in examination, but also because of the revolution or yes revolution that Compton's experiment had or brought in the modern physics. Let's say all of the so first of all, uh, Einstein was the advocate for particle nature of light in 19th century, and it was Compton's experiment which further proved that light can be considered as light can be considered as a particle interaction. Okay, particle, and you would see why this is true. So what did Compton found out? The major achievement of Compton was when we experimented with X-rays and elements with the larger number of electrons. We found out that when we strike X-rays to these elements, X-ray and electron just act like billiard balls. If you consider both X-ray as well as electron as billiard ball or just simple balls, then whenever you strike X-ray with some energy, it would go to this, it would strike to this, and it would uh, lose its momentum and some kinetic energy, and would transfer this kinetic energy to this, and this ball would cover some distance, right? It would gain this lost momentum and will cover some distance. And it was found that it is exactly what happens in the case of X-rays and electrons. So that means both act as a billiard balls. That means particle nature of X-rays photons was observed here. Okay, now, this was a major achievement in 19th century because 19 I think 1925, right? This experiment was done in 1925. So he found out that this X-ray has a momentum, okay, and a kinetic energy. And when a body have a kinetic energy as well as momentum, it must be a particle. And because of that, this momentum is being exchanged with this electron, and this kind of phenomenon is happening. Okay, and this type of phenomenon exists in real life. So that was the Compton's experiment. We would see it in much detail. So that's why Compton's effect and or Compton scattering has a major importance and significance in modern physics. Okay, let's see the derivation of Compton scattering. So we have here, so don't look to all of these, just look to the things that I point. Okay, so this is our incident X-ray photon. This is our incident X-ray photon. This X-ray photon have energy, incident energy to be E naught given by H nu naught, and the incident momentum is P naught given by H nu naught by C. It This incident X-ray photon strike to this raised electron. We have an electron here, and when it strike to that electron, before X-ray hit this electron has a rest mass of m naught, and it has a rest energy m naught c squared. When the X-ray strike it, it recoils towards another direction, and this recoiling electron has momentum given by mv, where v is the velocity through which the recoiling electron is moving, and the energy of this recoiling electron is given by mc squared. Similarly, this X-ray after striking this electron would scatter, and though let's suppose the scattering angle to be theta, then the energy after this of the scattered X-ray is given by E1, and it is h nu. Similarly, the momentum P1 is given by h nu by c, where nu is the new X-ray of sorry new This symbol nu is the new frequency of this scattered X-ray. Okay, so this is just the uh, description of what's going on here. Okay, now let's see the theory. For understanding the behavior of X-ray in this kind of setup, we need to take care of two things. First one is energy and second one is momentum. So we would use the conservation of energy and conservation of momentum formulas here. If you see the first expression, you would see that it is it's a conservation of energy equation, and where h nu naught is the energy of the incident photon, m naught c squared is the energy of the rest electron, and after that, after striking, this becomes the energy of the scattered X-ray, and this becomes the energy of the recoil electron. Okay. Similarly, if you see the conservation of momentum, then here we talk about two components of the momentum vector. So we will talk about two components. So that's why if you see here, this incident X-ray is along the x direction, so it doesn't have any y component. So we can say y component, or we can say that the sign component of this incident X-ray is 0. Okay, yes, sign component is 0, and the cost components are this. Energy has a cost component because it is just towards the axis. So these are h nu naught and h nu naught by c for the momentum. Similarly, for this rest electron, the since it is at rest, since it's a point, so it doesn't have any x-axis or x component as well as y component. Okay, so both of the component for this rest mass would be 0. Similarly, if you see this scattered X-ray, then this scattered X-ray can be denoted by this diagram here, where this vector represents the momentum of the scattered X-ray. And if you see the sign component of it, yeah, we can say cos component of it, it is given by h nu by c cos theta, and sign component is given by h nu by c sin theta. Okay. Similarly, if you see for this recoil electron, it is in the negative direction. So y-axis would be minus y-axis here. So the sign component would be minus of mb sin phi, and the cos component would be mb cos phi. Okay, so this is and if you consider uh, the energy component, it becomes the same thing. If we consider it's mc squared, then it becomes mc cos theta cos phi, and becomes minus mc squared sin phi. Okay. So we are taking into account two components of the vectors in for the conservation of momentum. So here, first one is the x component, second one is along the y component. And we know y component means sine component and x component means cos component. If you see here, first one, since X-ray is in the x-axis, that's why it remains as it is. Now this is a rest electron, so it doesn't have any x component, equals, now these both are the respective x components for the scattered X-ray and the recoil electron. If you come to this y component, here you see that X-ray is an x-axis, so it doesn't have any y component, so it becomes 0. Again, the rest electron doesn't have any component, so sign component of it would also be 0. 0 equals, and if you see here, it is the respective sign components for recoil electron and the uh, scattered X-ray. So this is what we get for the conservation of momentum. These two equations denote the conservation of momentum, and this single equation consider the conservation of energy. Now, one thing you should understand is that whenever we talk about rest mass and other mass or relativistic equations, relativistic mass variations, then we need to take care about those things by using this relation. M equals m naught by root under this Lorentz factor. Okay, now let's see further. After that, continuing to the derivation, we from the last two equations we get this equation and this equation, and we squared these equations and added these two equations. When we add these equations, we would add the corresponding terms, and by adding them, we get mv cos phi squared, mv cos phi squared plus mv sin phi squared equals this whole thing plus this whole thing. After that, we would like to do some simplifications, and since we can see here cos squared phi plus sin squared phi would give us 1, so we do the same thing, that we apply the squared to individual terms, and then we would get this and this becomes 1, and so we would get m squared b squared c squared equals, now here since both of the denominators are same, I can take single denominator, and from these two equations, since both have the same denominator, we can take all of these things as a whole, and so this becomes mv squared c squared, sorry, m squared b squared c squared equals this thing. After that, so this comes from the equations of momentum, x and y components of momentum. When I add them and actually when I square them and add them, this is what we get. Okay, further simplifying it would give us, is it clear? Let me make it more clear. Yes, so further simplifying that would give us this, because if you remember, we had cos squared theta and sin squared theta there, and those becomes 1, and we get just h squared and nu squared. So this is it. We rest the equation of conservation of momentum for a while, and we turn our focus, shift our focus to conservation of energy equation, which was this. So what kind of modification or simplification can we do here? First one, I want to take this in the right hand side, sorry, in the left hand side, and all of those other things into the right hand side. When I do that, I would get this equation, and I square it. When I square these terms, it becomes m squared c to the power 4 equals h squared, this whole squared, plus 2ab plus b squared becomes m naught squared c to the power 4. So this is the equation that follows through the equation of conservation of energy. So we have got two equations. First one is this, second one is this. What I'm going to do right now is I'm going to subtract this equation from this equation. When I do that, I would subtract the corresponding each element, since the right hand side has these two components. So I would subtract m squared c to the power 4 and m squared m squared b squared c squared, and equals to this component minus this component minus this component, plus this whole component minus this component minus this component, and m naught c squared. And wait a second, I think we would get plus sign here, because here you have a minus sign, so when I subtract it, this becomes a plus sign. So uh, this one minus becomes plus this thing, and this m naught c to the power 4 minus h square nu squared. Let's see what we get after this. Okay, so after this, what we do is we got this equation from the previous equation. Now, what we did here is we subtracted the similar terms, the same terms, and we got these terms to be 0, and we are left with these terms. It is easier for you to see and understand such kind of derivations rather than me speaking each and every term. So that's why I'm going to rush towards it. Okay, rush in this. That's why please I request you to see pause the video and see the equations and how the equations has been evolving. Okay, I'm just going to know I'm just going to direct you that what I did, and I'm not going to say all of those symbols again and again. Okay, so after this what I did is I got away from those same terms and I left with this equation. Now after that, since we know the relation between the mass and the rest mass, we can find out the expression of mass in terms of rest mass. And for that, what we do is what I did is I squared this equation and I get this. I multiplied the c squared to the right hand side and I took the LCM and I would get this. After this, what I did is after getting this expression, I squared both sides with c squared and I got this. Then after, I am trying to write this expression in terms of rest mass equation, and so when I try to write that, I got this expression is equal to this. So I can write m naught squared c to the power 4 in the place of this. So then our equation will lead us to this equation. So when I did that, you can notice that I have changed that value. Then since we have okay, yes, since we have m naught squared c to the power 4 on both sides, we can cancel these two terms. Then after, we know that we have got, wait a second, where do I have this? Yes, so wait a second. Yeah, these two terms, isn't it? H squared, I think we have h squared here, right? Okay, let me check. Yeah, so we have h squared there. Sorry, I forget to write that in the previous equation as well as this equation. So we have h squared here, and when I take this and this on the left hand side, I got this, and left and the right hand side we got this equation. So I cancel one h, both 2's, and I got to this equation. Not this, but rather whole of this equation. Right. Now after this, you can find out uh, the difference in between the 1 by nu minus 1 by nu naught by this expression. And we know if we could write that c here, this gives us lambda and this gives us lambda naught. So that is what I did. And on the other side, we got this equation, this expression. So this is what we were looking for. Now, since we have got to this equation, I want to revise what we have did up to here. So I think I should draw a diagram and try to. Yes. So we had we have a X-ray which strike to an electron, and the electron would recoil in this direction with the angle phi from the x-axis. Similarly, the X-ray after striking to this electron would scatter in this direction with an angle theta with respect to x. Now we have got our equation in terms of theta. So that's why we don't have any phi here. We are interested to find out the change in wavelength. The change in wavelength of this incident X-ray and this scattered X-ray. Okay, so we found out that this change in the wavelength is directly proportional to this angle theta. Okay, and if you further examine this equation right here, it says that it is inversely proportional to mass of the rest electron. So it means the more the mass of the electron is, or mass of the particle is, which scattered the X-ray, the greater the change is. Okay, no, no. The greater the mass, the lesser the change in the wavelength. So we have got some cases here. First one, let's suppose theta. Let's suppose, let's suppose this theta to be 0. That means even after scattering, it just goes along the x-axis. If that is the case, then that means there won't be no change in the wavelength. That means everything, every change that's happening in between the wavelength of incident and the scattered X-ray is all because of the work of this theta. Okay, so if theta is equal to 0, then both would have the same wavelength. There would be no change or no shift in the wavelength. Now after that, if theta is equal to 90, that means this theta just perpendicularly. So whenever it strikes, it just goes. For example, if let's suppose X-ray is coming in the x-axis, whenever it strikes to electron, it just goes perpendicular to the original direction. If that is the case, then we would get the change to be equal to h by m naught c, this quantity, and this quantity is known as a Compton's wavelength. Okay, the quantity, no, yes, I think it's called Compton wavelength. So if so I can say that when I say the change or shift in the wavelength is equal to Compton wavelength, that means, then by that statement, what I mean is that whenever X-ray strike to electron, it just went perpendicularly, or the scattered X-ray went perpendicular to the original direction. That is what I mean when I say that shift is equal to Compton wavelength. Okay. Similarly, we have at theta equals 180. In that case, the shift is the maximum, and shift is twice the Compton wavelength. These are some of the things that you should know beforehand. Okay, when we study about the Compton wavelength, or when we do some numericals about the Compton wavelength. So this is it about the theory. But up to now, we have just looked, or we have just studied the we have just looked at the scattered X-ray. We haven't talked about this recoil electron. So let's talk about this recoil electron. For the analysis of the recoil electron, we used the conservation of momentum equations from the previous slides, or what, from previous discussions. So we had two equations, one for the x component of the momentum and another one was for the y component of momentum. When I divide this second equation from the first equation, I would get something like this. Here, notice that what I have done here is I have divided these two terms. When I cancel these, I would just get tan of phi. This is how I got tan of phi here. And this is obvious. Okay. Then I got this equation when I took this in the other side. So this is what I got. Now one clever decision I did for the to choose the theta. I chose theta to be minus theta, and when I do that, I can get this thing plus this thing in front of it is plus and this thing is a minus. So I did this thing just to make nu naught to be positive and this nu cos theta to be negative. So I would be left with tan phi equals this expression. And I am going to rest that equation for a while, and I am going to choose and shift my discussions towards this, the result of the previous discussion. We have got this expression as a shift in the wavelength when the X-ray scatters. Okay, so what I did here is I wanted to bring nu and nu naught in this equation. For that, I did the obvious thing. First thing that I did here is I introduced C by nu naught. So C by nu is lambda and C by nu naught is lambda naught. I brought this C back here is C squared, and I left. I can say I can separate the 1 by nu because I want the value of nu, okay, in terms of nu naught, so that I can substitute that here. So for that, what I did is I isolated the nu and I got that in terms of nu naught. Now after getting that, I want to substitute that nu in our previous equation so that I can get the values in terms of nu naught. Okay, so for that, what I did is I just substituted this in the two places where nu is available at that equation, in that equation. So after this, I think I need some space now. Okay, it turns out that this expression is very hard for us to substitute and get the value of tan phi. That's why what I did here is I want to simplify this equation as much as possible. For that, I wrote it here, and I wrote 1 minus cos theta in terms of half angle formula, and it is given by trigonometry. It is 2 sine square theta by 2. Okay, now since wait a second, yeah, now what I did here is I divided all the both numerator as well as denominator by m naught, and when I did that I got this expression, and I considered this expression to be beta. So always remember that beta is equals h nu naught by m naught c squared. So uh, we get this equation. So this is a more simplified equation than the previous one. That's why we are going to use and substitute this value of nu in for the tan phi. So we would get this. Okay. Now if you see here, we got tan phi equals nu naught sine theta by the same thing is the denominator, and mu naught times this denominator for the LCM minus mu naught cos theta minus mu naught cos theta. Denominator is same, so we can cancel these both denominators, and we will be left with this numerator and this denominator. Now, since you know that if you see here, all the terms have mu naught, so we can take a common mu naught and cancel this with the numerator. So we got rid of this mu naught too. After that, what I did here is I use a formula for the half angle formula of sine theta, and it is 2 sine theta by 2 times cos theta by 2. So that's why I wrote 2 sine theta by 2 times cos theta by 2. Here we have 1 plus 2b sine square theta by 2, and minus of mu naught is already gone, so we are just left with cos theta. Now we know that cos theta can be written in the form of 1 minus 2 sine squared theta by 2 in from the half angle formula from the trigonometry. That's why when I substitute it, this 1 and minus 1 are cancelled, and 2 sine squared theta by 2 is common, and we are left with 1 minus minus plus beta. So 1 minus 1 plus beta is beta plus 1, same thing. Then after all those things are cancelled, and we will be left with cos theta by 2 as a numerator, and sine theta by 2 as denominator. So this becomes cot of theta by 2 by 1 plus beta. So this is the value that we were looking for tan phi. So turns out that tan phi has a value of cot theta by 2 by 1 plus beta, where beta is h mu naught by m naught c squared. This is the value. So from here we can find out the angle by which the electron recoils when it is hit by or struck by an X-ray. If you want to further know about the kinetic energy of the recoil electron, then you can find out it is Ke equals h nu naught minus h nu, and substituting the value of h nu is this, if you can see, is this, we can know that mu naught plus 1 plus 2 beta sine square theta by 2. So from here, 1 minus 1 by 1 plus 2 beta sine square theta. So I will be left with 2 beta sine square theta by 2 by 1 plus 2 beta sine square theta by 2 h nu naught. This is the kinetic energy of the recoiled electron. So with this, we complete our lecture on Compton scattering, as well as the whole chapter X-rays is completed. Thank you so much for watching this. I hope the videos that I am making are helping you to understand the course material.